Alright, hey guys, and welcome back to another AP Physics C video. Today we're going to be just working on one of those major derivations, a bit of a calmer one today, but nonetheless a major derivation. It's going to be the induced electromotive force on a sliding bar that's sliding on parallel conducting rails, which actually form a circuit. So let's just jump right into this derivation here. This bar is conducting with length L, where L is actually the width of the parallel conducting rails as well. And the bar also has resistance R, and there's a magnetic field B throughout the entire region within the parallel conducting rails that points out of the page. And the bar is moving with a speed V, so the velocity is this way. So let's just jump right into the derivation. Intuitively, whenever you have a magnetic field, whenever you have an induced voltage, you're going to want to think of Faraday's law, where we say, well, the induced voltage, right, is the absolute value of the negative derivative of flux with respect to time, of course. Right? That's just the law. Something you should know. It's on your equation sheet. The reason why it's absolute value of a negative is because this negative serves to show that Lenz's law exists, right? Lenz's law is a part of this magnetic phenomenon. Basically, Lenz's law is saying that whenever you have a changing magnetic flux in a system, or like a closed loop, that closed loop will self-induce some current in order to create a magnetic field that will oppose the change in current. So that's why the change in magnetic flux. That's why that negative is right there. But these absolute value signs are there because we don't care if it's negative or positive. We just want the magnitude today. But if you guys have any question about that direction of current, please put them in the comments. I'd be more than happy to answer them. But today we're just going to derive the magnitude. So now that we have this negative derivative, we need to think, okay, well, what is flux in this instance? So let's write that classical definition of flux. We'll say magnetic flux is equal to B dot A, right? Simple enough. Our area, right? It isn't, well, our area actually is changing. Our magnetic field is not changing, right? Throughout this entire system, right? Throughout this entire scenario, the magnetic field will always be constant, right? That was a given. So when I do the dot product, I don't need to worry about our magnetic field changing. So I don't have to do any integral calculus or anything like we did in some of those earlier videos. So I'll say BA cosine of the theta between B and A, right? That's how the dot product works. And we'll just get rid of this right-hand side and evaluate the cosine of the theta between the two. So the cosine of the theta between the magnetic field vector and the area vector is actually 0 in this instance because this area that we want to find the magnetic field or the magnetic flux through is pointing out of the page, right? The area vector of that surface, that area, is pointing out of the page, right? And as is the magnetic field. So if for a side view, here's the area vector, and the magnetic field is in black. If I put them side by side, oh, well, guess what? The theta between them is 0, right? There's no angle between them. So therefore, the cosine will be 0, and this right-hand side will just turn to 1. And 1 times anything is itself, so we don't need to worry about that. We can just cut that out. But even if the theta wasn't 0, all you would do is maybe add a constant to your magnetic flux equation, right? You wouldn't have to do anything besides that. And even if it was 180, right, where you would have negative flux, well, we want the magnitude. And AP Physics C will often only ask for the magnitude. So really, there's no situation in which you should be freaking out over the dot product. But back to what I was saying earlier, we want the magnetic flux through this left-hand side, right? And you might be asking, or you might have asked, well, why, right? The reason why is because on this left side, there exists a closed loop in which current can flow. That's the only loop that exists because these squiggly lines on my right-hand side show that these bars, these parallel conducting rails actually extend to infinity, right? There's no closed area in which there's a changing magnetic flux. The only changing magnetic flux is on this left-hand side. The magnetic flux on the right, well, that extends to infinity. So, well, guess what? The magnetic flux, well, it's pretty much infinity. So you really don't need to worry about that. So back to what I was saying, we need to now figure out an expression for that area of the left-hand side, which has actual changing magnetic flux. And I know area, right, is going to be length times width, right? So let's identify the length and width. Well, in this instance, the width over here is what I'm about to highlight in pink, right? The width actually is L, which might be a little bit confusing, but don't get it wrong. L is just a given constant, right? It could have been any letter, but in this instance they picked L, so don't freak out. We'll just write it like it is. We'll say, well, the width here is L. That's it, really. So now we need to worry about, well, what is the length? But in this situation, you can see that this length is changing, but I'm going to give it this arbitrary value x, right? Because I'm not going to define it with a constant. No, I'm going to say x. X is my width, and x can be changing, right? Um, so that's what I'm going to say. I'm going to say my length is x. So my total area will actually be Lx, L times x. So now I can sub that in to my magnetic flux equation, and I'll get the magnetic flux is equal to BLx, right? Simple enough. And now I'll bring back Faraday's law, and I'll sub in my expression for magnetic flux, which was BLx, and derive from there, right? So if you see, this is just a pretty simple derivative. If we identify our constants, like an integral, we can pull out those constants. So b and l are constants, right? But x is not a constant because in this instance, x is changing with respect to time. So now this induced voltage becomes bl dx dt. And now this is looking a little bit familiar because what is on our right-hand side? Well, guess what? Dx dt is velocity, v. So the induced voltage is actually BLV. And that is your final expression for voltage. Hopefully that made some more sense. It's a little bit more difficult to grasp that this x is changing as a function of time, which normally you would see that phenomenon, but it's kind of hard to do with a still image. But hopefully it made sense the way I explained it. But this is one of the more simpler derivations, but I went through it slowly so that you guys could have a conceptual understanding. But on this AP exam that you might be taking in 2026, as of now, you should be able to do this more quickly, right? Because this is one of the more MCQ heavy questions, but it has shown up on the free response before, and I would expect it to show up again. So be ready for anything, and I hope you guys enjoyed this video and it made some more sense. So catch you guys in the next one.